Okay, so hello everyone. So welcome to our this week Rogers Efficiency Seminar. And today we're very glad to have Siddharth from the University of Notre Dame to give us this talk about the in and the near memory computing for machine intelligence. And Siddharth right now is an assistant professor in the Department of Computer Science and Engineering at the Notre Dame. Prior to that, he was a postdoc fellow in the UC San Diego, and where he also obtained his PhD degree. And his research focus on the co-design of the customer hardware and algorithm for machine learning adaptive signal processing. And actually, I know that you have a few words included the NSF career words, but you did not put that in your bio. But I want to let everyone know about that.
Thank you.
Okay, yeah. So let's welcome our today's speaker to give us this talk opportunities and challenges for in and near memory computing for machine intelligence. Okay.
Yeah, thank you. So yeah, thanks, Paul. Actually, I've been following the seminar series you've set out since I started as a assistant professor. So I was always like, oh, when am I going to receive that invite from Bo? As soon as Embrain FG got it, who's a lab mate of mine, I was like, okay, and I'm gonna wait until I get it as well. That's how you know you're doing good work when you get that invite. So yeah, I think this sort of image, this is from the documentary that DeepMinder put out. Right, this image, I think, in some ways defines the era that we're in right now. You see Lee Sedol over to the right, and you see the representative from Google DeepMind making the moves for AlphaGo. And this was, I think, the second game where AlphaGo made that move 37. Right, and then move 37 was where um, it was sort of this very surprising move that the AlphaGo was making, that the commenters and everyone who was analyzing the board thought, oh, this was a mistake. But turned out that it had a pretty large implication, much further down the line. So it was one of those moves that people still study. And so this was probably one of the first times when I think lots of people started feeling that, oh no, deep learning is actually going to have a bigger impact on intelligence than what the expectations were. Now, this is interesting also because we looked at this and saw, okay, AlphaGo is beating a human. Well, I'd go for the first time. At the same time, if you look at the resources available to AlphaGo, which is many kilowatts, and the resources available to LiCiDo, which is about 20 watts, right? We still see that despite that superhuman capability that AlphaGo might have at that one narrow discipline, um, in terms of efficiency, biology still has it beat. And I guess that's where I feel it makes a lot of sense to look at how do you get, how do you figure out what is the best possible you can be, right? Um, it feels like biology has this extreme efficiency that we, in our uh, effort to develop intelligent systems, have not been able to copy as yet. So this is an example of micro wasp. It's this small insect on the right. It's a microscopic insect. It's actually smaller than many single-celled protozoa. So something like this, right? Um, this micro wasp has about 7,500 neurons. Right? It's not very big, but even then, it is actually very capable of acquiring food, moving, acting on its environment, learning in the field, processing inputs. It's actually, from some considerations, still more advanced than modern robots and autonomous agents are. Now, given the efficiency with which it is able to do all this, just 7,500 neurons, right? This still means that we have a long way to go if we wish to develop autonomous systems that can have the same efficiency and impact that something like biology can. And so I feel in order to actually develop artificial systems that not only have the complexity and capability of something like AlphaGo, but also the efficiency of something like what biology can give you, we need to be developing new forms of computation, new forms of hardware to implement that computation. And when I'm saying computation, I'm being maybe a little bit more broad in general, but we need to rethink even things like how do you sense? How do you process what you've sensed? How do you act on what you've sensed? Right. So biology doesn't really distinguish between algorithm and hardware. It's very strong co-design. And I feel very strongly that that is the way to get that kind of efficiency and capability. It is to very strongly co-design both the hardware and the software and the algorithms. So that's broadly what I'll be talking to you about today. I'll be talking about how can we rethink some of the computational primitives. I'll be talking a little bit about how, some new work we're doing in terms of how do you get new types of signal processing capabilities using novel computational primitives. And I won't be talking too much about the algorithms just because of time, but I'm very happy to talk about it. So in the first part, I'll talk about the accelerators. So how do you build hardware for these new types of algorithms? Now, there's a broad range of algorithms that people have been working on, mostly focused on tensor algebra processing. Um, there are some cases where, talk about this to many people at these companies, and they'll say, oh, why do you care if it's efficient? Just put it into the cloud. We can have very massive GPUs in the cloud. Why do you care about small mobile processors? The answer for this, I feel, is maybe threefold. So over to the left, we're talking about robotics, right? And although teleoperation systems where you can go and transmit everything you're seeing and doing to a remote operator, and that person can operate the robot, although that's become very, very popular right now. I think for privacy reasons, you might still have very strict situations where you want your robot to be able to operate on things instantaneously with very little latency, which would require that it's doing it locally, right? So it's very difficult for, in every situation, a robot to always be communicating to a remote location, getting information back from a remote location, and only operating in that teleoperated circumstance. The other one can be mobile devices. So for every one bit, if you compute upon that bit locally, you actually are going to be about 10 or 100x more efficient than if you transmit that bit wirelessly. So if you have a mobile device and you care about your battery life, I know I care about the battery life of my phone constantly running out. I need to I would like to maximize the amount of compute I can do locally. Now, there's always going to be a balancing act. Um, if I record my voice, just transmit that voice recording over to a data center. The data center then, unzips that voice and decompresses it, runs a very large language model to process it, and then sends back an action. Then I'm only transmitting a few bits. So this is obviously very, very small in terms of energy cost versus running that massive language model. So there's always going to be these trade-offs. At what point do you offload, or what point do you do local compute? But for phones, for VR glasses, all of these sort of entities, there are many cases where I want to do my compute locally. The other one which I like to point to, it came about actually after a concert that happened in San Francisco. So there used to be this startup called Cruise, CRUZ, I think. And they were operating this autonomous taxi in San Francisco. And um, they had this thing where they transmit all of the camera information to a centralized server. The centralized server would do all the processing, and that would help the cars operate. So during this concert, the everyone wanted their cruise taxi at the same time. So the cell networks got overloaded. When the cell networks got overloaded, the cars couldn't get enough bandwidth to actually transmit the video information and enough information over to the server. And so all the cars would actually be waiting on the side with their blinkers on because none of them could safely operate. So under those sorts of situations, it actually helps a lot if the car could have local processing and have some local intelligence rather than always offloading to these large centralized systems. So broadly, for modern tensor algebra workloads, especially when response time is critical, there are many cases where you would like local models. So that's the more accurate statement. And this is true even for most of these contemporary thinking sort of models. Now, I had developed this slide, let's say, sometime over the summer, and I think some of this might already be older news, right? GPT-5 came out, which might have different performance on some of this, but the trends still hold. And the key trend to look at is that increasing performance in terms of this pass-one accuracy, right, requires exponentially more compute. So it's linear on log scale. So that means that you need to spend exponentially more compute and inference in order to improve the performance. This seems to be a trend that's holding steady, I think, across a set of different providers. So this is just showing what OpenAI has. The one on the left shows what Google has. But broadly, I think every model, major large language model developer out there seems to show the same trend that you need to provide training and inference with exponentially more compute in order to still continue to get linear improvements in performance. Given that, it seems very prudent for us to think about cases where we can improve the efficiency of our computation for these sorts of tensor algebra workloads, which include language models. Now, this is work that a friend of mine, where Vaughn had done during his PhD. And one of the interesting things I found from this is that not only are these different types of models very, very, very heavily memory dominated, they actually, this domination of memory bandwidth actually still holds for modern systems. So during the decode phase of a language model, it's actually pretty much dominated by memory bandwidth and not really impacted by compute intensity at all, right? Um, but don't have to only think about language models. There's many different types, especially if you're trying to deploy things on the edge, especially if you were trying to put something on your glasses or on your cell phone. And for most of these systems, the memory hierarchy actually dominates in terms of where you're spending your time and energy. So optimizing that seems to make sense. Right? That's a good lever to push on. Now, I'm going to just define some taxonomy here so that we're all talking about the same thing. Um, the term compute in memory or near memory, this is just used in many different places, and everyone means something slightly different. So I'm just doing this as a way to make sure that you and I are talking about the same thing here, right? So typical system is your one-dimensional system. You put your memory very far away from your compute, very far away on nanoscale. These are two separate entities, and you're constantly shuttling data or shuttling bits or information back and forth between the memory subsystem and the compute subsystem. Processing in memory is actually a term that I've seen being used both in industry and in academia, specifically to do with DRAM-based computing. So I'm going to continue the trend. If I'm talking about PIM, I'm going to primarily refer to that with respect to DRAM-based computing. The other one being in-memory compute or computed memory, which is often for this SRAM style or RRAM style bitline-based computing, where you do analog computation on the bit line of the memory itself. And you can use that to implement either matrix vector multiplication or some Boolean operations. There's also the term compute near memory, which is often nowadays the term is somewhat related to digital in-memory compute or digital computing memory, where you create your memory subsystem and maybe you modify either the memory cell itself or the sense amplifier in order to implement these custom operations. You're not doing analog computing in this case, you're doing Boolean operations primarily. Now, the idea itself is not very new. People have been doing this for, well, since 1989. So I think probably since before I was born, right? This one on the left is a system that was put out by Intel. In fact, if you look at it, this looks a lot like a lot of modern systems as well. There's multiple synapse arrays. You sum them up through analog transimpedance amplifiers, neurons. You implement a nonlinearity using sigmoids, and you can then feed this out. I believe actually there's even a paper where, so this particular chip was programmed by Jan LeCun and all at Bell Labs at that time, where they were able to get something like 4 bits accuracy or 8 bits accuracy out of their neural network running this chip. Then there was a DARPA project, which I think Dave Patterson and all had completed it. And so they had this IRAM project, right, where they were trying to do DRAM-based computing, where you rethink computer architecture again, right? Why should DRAM be separate from your logic? What happens when you merge it? So they had this intelligent RAM system. This is 97, right? So before I was an undergrad. I think given a lot of grad students and undergrads and all attending this talk, probably before you guys were born, right? Then there was stuff out of Hopkins as an example, where they were doing this kernel tron system. They were doing a DRAM array with ADC arrays, and you could do support vector machines implemented in these types of systems. This is 2003. So this is not the concept of sort of taking machine learning style systems, merging them with memory and compute and rethinking architecture in this way is not very new. In fact, it seems to go really well with neural networks specifically, machine learning specifically. It's just there's always been more things to do, right? More core design to do. So there's always more work that needs to be done before it's ready. Now, there are, of course, some limitations to analog computing. And this is one of the reasons why it's never taken off the same way. So over to the left, this is from Rahul Sarpeshkar. where he defined this crossover point between analog and digital computing on when does it make sense, when does it not make sense, and he sort of looked at it from the perspective of 1/f naughts. Now, I don't think the exact crossover point in A matters. So this could easily change based on different technology nodes. What does matter, I think, broadly is the trend that as you get to higher and higher uh, output signal to noise ratio requirements, you will be better off doing digital compute purely because digital scales much better along the output SNR axis. On the other hand, on the input SNR axis, it looks like analog compute actually scales quite well, right? So this one down here shows that my input SNR, as long as it can keep on going up, and provided that my output SNR is, let's say, over here, 60 dB below my input SNR, which means I've done some computation, I've extracted only key information, and that key information is, let's say, 20 dB worth or 20 dB worth of information. So that would be approximately 4 bits of information, right? Then I can actually sit at 1,000x better energy efficiency if I'm doing analog computing. But this is only under this specific scenario, right? I have high dynamic range inputs, and I'm extracting a lot of information through computation, specifically linear computation. Um, there's also much more recent work. For example, Boris Merman, he done some work on how does bit precision scale with analog and digital computation, right? And you see it sort of follows a similar trend to what Rahul's work had earlier on. Broadly, I think all of these efforts seem to indicate that as long as you're doing low precision computation, analog computing can scale. It's only when you have to do higher and higher bit widths and higher precision that digital computing starts getting much better, scales much better. And this sort of holds even when it comes to looking at what actual products are doing. So I've highlighted on this chart, which is really cool out of Tsinghua University, where they are trying to benchmark and look at the landscape of all these different accelerators that are out there, right? So they've done these isoclines for, hey, let's say I care about 1,000 TOPS per watt or 100 TOPS per watt, so on and so forth. What systems so far out there can actually deliver that type of performance? And looks like the only systems able to give that kind of performance are analog systems. If you're looking at the 1,000 TOPS per watt isocline here, but these are all purely prototypes. These are not products. As soon as you're looking at mixed signal products, so something like this, right? Oops, sorry. Something like this, right? Your efficiency drops down to approximately 10 TOPS per watt. In fact, very rarely do you get systems that exceed, that even approach the 100 TOPS per watt numbers that you see often in literature. So very quickly, I want to talk a bit about the more common approach for computer memory, which is the digital in-memory compute, digital computer memory systems. I feel there's two broad categories of systems that people make. These tend to be either extremely bit serial, such as this work on the top left, which is probably one of the most bit serial, sort of dense, compact approaches you can imagine, where you have a single bit adder per column, and you sort of pipeline it across columns in a memory array, and you're able to get extreme density, right? Your single full adder is nothing in comparison to your memory array. This can get you really high, um, let's say, tops per millimeter squared. Now it's slow because it's bit serial, so it's not necessarily the best tops per millimeter squared, but that's what you're sort of going for in this approach. The alternative is much closer to what TSMC and all have been doing in their recent work, where they've been doing these massive, fully parallel adder trees, where your memory cell has a NOR gate attached to each cell, right? And you broadcast the multiplicand and you in parallel sum up everywhere. And I believe actually these systems are now in production. Some of these are IPs in a recent MediaTek Dimensity processor. And so this seems to be the approach that more modern systems are taking. And this, of course, goes more towards extreme throughput, right? If you sort of squint at the numbers over here, they're talking about being able to do 4,000 tops per millimeter squared per bit, right? So this is extreme throughput. Everything is parallel, right? This is all doing 144 multiply adds in just a couple of clock cycles, right? Followed by these massively parallel reduction units. Now that maximizes your parallelism and maximizes your throughput, but of course at the cost of area. And I think pretty much every other digital in-memory compute system sits as a trade-off between this. It's a trade-off between how parallel do you want to do your compute, how serial do you want to do your compute, and how compact can you make it. And in our own work, for example, we had this that we've done in 12 nanometer global foundries design. Even in our own work, we see that if you're not careful, right, again, your multipliers can start taking about as much area as your memory system. Now, of course, for these types of digital in-memory compute systems, you don't typically have sense amplifiers on your SRAM line. So that means you can't have really large memory arrays. So you are forced to sort of make these trade-offs such that you're sitting at really tiny areas overall in terms of the memory macro size. So this particular design was doing a sub-threshold implementation, and we achieved reasonable numbers, but this is primarily simulations. The chip itself is currently being tested right now. So hopefully these numbers hold up. Now I want to talk a little bit about compute using resistive memory, and I'll focus a bit of my talk on this particular type. So the general idea for something like this remains, I would say, pretty common nowadays. You have a matrix vector product you wish to do. You encode the weights of your matrix as the conductances of, let's say, a resistive RAM style memory array. And then in parallel, you activate all of the memories, apply voltages along the periphery that encode the input that you want. And that voltage through a resistor sort of sums up linearly along these bit lines. And that you can then sense. And currents just sum up linearly. So this makes addition to be a very nice operation here. You can add up many, 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 serial, many, many, many wires in parallel, all for quote unquote zero cost. And this lets you very quickly do very wide vector adds for very cheap. That's what this whole thing focuses on. Now, there are also SRAM-based design, something like this. Um, this doesn't rely on these RRAM style systems, and you can use switch cap style techniques where you sort of move charge over from the SRAM into a small capacitor over there, and then sum that up along the midline, and then you can use an analog to digital converter over here at the periphery to sort of capture that result. So this sort of switch cap approach actually has become quite popular. Naveen Verma and Naresh Shambhak, have done a bit of work on this. And I think Naveen's even got a company on this called Encharge right now. Now, of course, I showed you one sensing modality, so that's voltage mode. You can also do current mode sensing. We did some work on looking into for different types of designs, which one makes more sense for the particular type of design we were looking at. It seemed that we get this nice normalization effect when you do voltage mode sensing, which meant that you got better normalization of your bitline value independent of the model type. So over here, actually, it's quite interesting to see that different model types have different dynamic range in the bitline value. And the specifications of your analog to digital converter typically will depend on the dynamic range of this value. And so by being able to normalize this value, you can try to have a more general system that is more independent of the model type itself, making it more generally applicable. Now, why talk about ADC so much? That's primarily because analog to digital converters are the limiting factor when it comes to um, power efficiency of in-memory compute systems. So ADC energy is exponential with resolution, which means you either, if you're thermal noise limited, then you actually face a 4 to the number of bits sort of penalty. If you're not yet thermal noise limited, then you hit 2 to the number of bits penalty. But as the recent trends show, most systems have been thermal noise limited. So you are going to be heavily penalized for using high resolution analog to digital converters in these systems. And it looks at the moment as though most of these systems are primarily dominated by the efficiency of the ADC that they have. So anything that can improve the efficiency of the ADC is going to be a huge plus. So I'm going to talk a little bit about our particular chip. This is work done with Stanford and Tsinghua University, and and UCSD. So this is when I was in UCSD, and once I was faculty, my first student actually worked also on the same chip. This is a 130 nanometer integration of resistive RAM with CMOS and all, integrated as a 256 by 256 neurosynaptic array onto one die. And we were then able to sort of scale it up into multi-core design. So broadly, this is what the system looks like. We have a special layout of our system such that we're able to do an in-place transpose purely through switching certain connections on and switching certain connections off. We do a very compact analog to digital converter design, basically a inverter-based integrator, which lets us be really compact such that we can then interleave this ADC within the memory array itself. So this is not something you would typically do. Typically, you would have very dense memory arrays and then ADCs outside of that. But we found you can actually have better performance overall by being able to do this interleaving of the system like that. And we had this fab a while back. We got this tested. right? In our particular case, because our devices had these really high voltage requirements, the word line switching uh, actually dominated in terms of energy. And we'd applied this for a bunch of integrated fire style workloads, including a restricted virtual machine at that time. And um, yeah, we got some pretty reasonable performance out of it. We then managed to scale it up, doing 48 cores, and then run multiple small quantized models on it. And we were able to get accuracy to approximately 3 or 4 bits quantized model performance. So I'm gonna just take a sip of water and ask if there are any questions for the time being. No? Okay. So yeah, broadly, we were able to figure out a way by which we can take that switched inverter-based system and apply multiple steps of operations to it in order to extract more output precision out of it in a multi-step ADC fashion. So similar to what I was talking about earlier on with digital in-memory compute, where bit serial can be much more compact, while full bit parallel obviously takes more area but higher throughput. So we also tried to see if we could do a semi-bit serial, semi-bit parallel approach with the kind of system we were developing. And that's what let us actually perform at the level of software systems as well, even for these recurrent models where if you're not careful, the error accumulates over multiple time steps. So we had learned some lessons, right? We had upwards of 5 years of design time for this kind of a system. It took really long time. We had sort of many things that you really need in the system, which were academic design. We didn't have the time and capability to implement, very complex networks on chip, very complex buffer management systems. And some DNN layers did not map well onto these RAM arrays. And so we needed other types of systems to be able to sort of integrate everything together into one actual final product like accelerator. And so that's sort of one of the things I've been focusing on of late, which is can we develop methods by which we can automate the generation of many of these LPs that we need? Can we develop application specific analog to digital converters? Can we develop automated mappings? How do you co-design the model so that there are very few layers that actually need things that the computer memory system is not good at? Can you avoid those layers at all? Because that's broadly what we've been working on, broadly what I'll try and cover in the remainder of my talk here. So I'm going to talk a little bit about the particular ADC that we had designed and how we were able to get this to give us good performance, including on multi-bit systems. And the idea broadly, as I'd sort of alluded to, was that we were able to break down the process into a multi-step system whereby we could sweep the reference integration voltage over time. And that allowed us to change this from just a ramp ADC into almost a SAR-like system over multiple cycles. And based on this, we were actually able to uh, push this system to be much more accurate and compact than it otherwise would have been. And these sorts of, I'd say, novel ADC designs, I think, are required. These are very unconventional ADCs that you might need to implement in order to create more compact and efficient in-memory compute systems. We need methods by which we can actually estimate, how do different detailed circuit design decisions impact us at a higher abstraction level. And to do that, we've been looking into high-level architecture descriptions and workload descriptions that can very quickly estimate the performance at the system level without really um, doing detailed implementations of any of these systems. Now, there's multiple such systems that exist. We've been working with some of these as well. The core idea is to help you do very rapid system design without having to design individual ADCs, right? Because you can imagine detailed circuit design of one ADC is already actually a PhD student working for multiple months. Using that then for a full architecture is actually quite difficult. So trying to absorb some of that, abstract that, and do this from a more top-down perspective. So there exist tools that help with this design space exploration. A lot of them focus primarily on doing this for digital systems, right? If you imagine, and this is from Time Loop and Accelergy. So this is from talks that Joe Lamber and company have given on this before. So if you imagine taking this sort of a loop nest implementation of what a convolution looks like, and just reordering these for loops, you can actually see that they describe when and what type of memory accesses you're doing. And as you remember, I mentioned that the memory hierarchy can be quite dominant when it comes to your energy expenditure for these different accelerators and different models. So by reordering memory access across the hierarchy, you can actually severely impact the efficiency with which your system can execute there. And so doing something like that, but also for in-memory compute, I think is a huge need. And doing it in an automated way is currently not completely handled. Yes, this is from the Time Loop paper by Anshul Prashar at ISPAS 2019. And the key thing here is this number, right? In the histogram over to the left. Out of all of these different mappings that we showed, which are primarily just reordering these loop nests, only 10 of them are close to optimum. You can in fact have a massive, almost 19x change, 20x change in energy efficiency simply by picking the wrong mapping. So doing this in a systematic way actually is quite important. We've been working in this area as well. So we've been trying to do this rapid design space exploration for these types of mappings. I won't go into this in a lot of detail, but mostly to show that if you're not careful, then you can lose, you can have, let's say, computer memory arrays or digital PEs that are underutilized. And usually the way people get around it is by doing hand optimizations of these mappings. This actually is from the original Iris paper out of Vivian and Joel Lamer's work. And we were able to develop systems such that you can get the same benefit of hand optimized mappings, but in a completely automated way. And so you can get the same utilization with improvement to the energy delay product as well. And our particular system, which we call Ruby, was able to perform much better overall across the board, right? Across different architectures and across different models as well. So this is from Deepbench. So these are all different types of model layer shapes. And this over to the right is the geometric mean of the overall performance. And so you want the NG delay product to be lower and cycle to be lower, which is fortunately what we were able to get. And so, even across different architectures, we're able to improve the performance on the Pareto frontier. As you can see, in red, which is our Ruby mapper, it actually is able to occupy the frontier much more regularly than the typical baselines. And on average, we improve the Pareto by 20%. So this, of course, usually you think about this purely as applying to digital systems, but it also applies to in-memory compute systems, right? So we've been looking at this from the perspective of in-memory compute systems, and being able to rapidly do these estimations and efficiently figure out before we actually tape out a chip, hey, what's the details of the chip that we should be taping? Oops. This, see, okay, yeah. So we've been developing these updated systems. We call ours Uber, and right now we seem to be getting some benefits from our system. Seems to be maybe a little more compute heavy, but also able to improve our performance over here. So, good thing. And based on that, we've done some additional work where we've been able to develop, using the same 12 nanometer process I'd mentioned earlier on, a more advanced node-friendly in-memory compute system where we're actually targeting now language models, and we can do compact mixed precision operations within the SRAM array with a shared analog to digital converter, and rescale that output with a floating point multiplier as shown here. And this sort of gives us pretty efficient result, I think. Still dominated by the analog to digital converter. As you can see, 40% of our power still goes in the ADC. But the total power actually for I think this is 200 megahertz clock, still quite low. It's around 177 microwatts. And yeah, I think this slide's not showing up well, but in our estimations at the moment, while accounting for the model quantization and the ADC noise, we're still able to actually approximately match the baseline performance that we'd be looking at. So this is for multiple models across both REFAI and MMLU. Sorry, excuse me. I think my screen is stuck. Hello?
Hello, hello.
Hi, Bo, I think my screen got stuck. Could you hold on a minute? Sorry.
Okay, no problem.
Okay, yeah. Sorry, man.
Yeah,
Sorry.
it works now. Yeah, it works now.
Okay, good. Yeah. Yeah, so the next question becomes, can you do better? Right. So we've been looking into sure, we do one layer at a time optimization. We do our in-memory compute programming, processing element. But what does that look like at the scale of like the larger system, right? So the question becomes, can you do better? Now, as I mentioned, most of your energy comes from moving data in and out of DRAM, right? In-memory compute can reduce the amount of data movement, but it can't bring it down to zero. And unless your on-chip memory is as large as DRAM, you still need to move data in and out of DRAM. So we've been looking into seeing, can you develop data flows for in-memory compute that can take advantage of operator fusion the way you have with standard GPU kernels in order to even further minimize the energy impact of these systems. And so consider transformer style network like this shown over here, and look at these cascading activations that are generated. And what we do is run a genetic algorithm that calculates all these cascading activations and tries to minimize the amount of data that we need to offload outside the chip itself in order to maximize, in terms of improve our energy delay product. So this is what our genetic algorithm sort of does. It doesn't really take too many different operations. And when we ran this for a simple convnet, I think this is ResNet 18, we're able to get a substantial improvement across a bunch of layers. So the colors here means that we were able to remain entirely on chip without having to sort of go off chip and recompute or refetch something. So you can see for the initial sets of layers, you can actually remain on chip for a much larger duration. And then after that, you can fuse maybe 2 layers at a time. But of course, there's individual layers sometimes that you can't fuse. Overall, though, this lets us improve performance by up to 1.3x. Like this is purely from PyTorch layer to performance estimation. And we can do this across multiple types of in-memory compute cores with multiple types of sparsity requirements. All of this lets us do very strong co-design at a higher level. Right? So this is broadly where we're looking to go next. Can we explore the sort of map space assignment for much more complex heterogeneous systems? We have the beginnings of this done right now, I think, but always looking to collaborate with people and do more complex work here. So there's many core design optimizations that remain. I think sparsity and pruning are currently still hotly debated and really important topics. Doing ADC aware optimizations, I think, is actually still not done as much. And so that would be something I'd be quite interested in doing. So I don't think I'll be able to get to this, but I'd love to take questions.
Okay. So thank you, Siddharth. Thank you very much for your wonderful talk. And any questions from the audience? So actually, I have several talks. I have several questions, but I would like to ask you ask first. So you can either.
Hello, Professor. Lovely talk. I'm just curious, like, for the PyTorch, like layer wise, like you're basically trying to fuse layers, right, using the genetic algorithm.
Yes. Yeah. Yeah.
So could you just clarify, like, what do you mean by like improvement over PyTorch or something like that?
It's not improvement over PyTorch. Sorry, this is improvement over layer by layer operation.
I see. And this is purely coming from like having to access the memory less often. That's
Yes. Yep.
okay. Can I read more details in the paper? Is this published yet?
This is on archive. I can send you the archive.
Okay.
The preprint.
That should be great. Okay. Thanks. This was really
Or
interesting.
actually, if you don't mind, could you send me an email so that I can send it to you? Because I don't have your email.
Of course. I'll get in touch with you. Thank you so much.
Some other questions from the audience? So maybe I can ask some questions first. So very informative talk. So actually, I know that you work on the different types of the in-memory computing, right? So
Mm-hmm.
and we know that so this area has been kind of the well studied in the past decades, right?
Right.
In the past 2 decades, right? And we know that so previously we have like those that uh like the convolution net and so on, the LSTM, and right now we enter the area of the generative AI, the LLM, the diffusion models, and a very interesting the trend recently that so those like the like near DRAM computing, in DRAM computing, and also together with those the heterogeneous the integration, right? So
Yeah.
we know like the MediaTek recently they have the new chip that actually they have to integrate both the PIM accelerator plus the traditional ASIC accelerator for the NPU. So right now with this trend, so do you think so? What is right now the new emerging challenges? So for the especially for the hardware designers that when we want to like to leverage the power of the in-memory computing.
Yeah, so I think one of the actual challenges right now seems to be, I guess, let's break this down into three things. First, model training. Second, yes, model inference deployment. And third, sort of uh, chain of thought kind of trait, right? The thinking layer stuff. So I feel so far in memory compute, people have primarily focused on model inference, right? But model inference is mostly bandwidth limited, and there's no reuse. So once you've fetched, let's say, a KV cache, right, you don't really get much reuse out of it. So you're not actually compute limited at all. So I'm not sure how much benefit you get from in-memory compute as a specific way of doing it. I think we need to come up with more interesting recompute type methods. I know that more earlier on in the year, there was some work where people said, oh, instead of storing KV cache and fetching it, why don't we recompute parts of KV cache? Because compute is still cheaper than memory fetch, right? And that actually, even on a GPU, brought people some advantage. So I think revisiting techniques like that, where just because a KV cache exists doesn't mean that we have to, treat it like a memory cache, and we can actually recompute elements in there if our compute operations are cheap. And those types of things probably need to be relooked at. Second one is, I think we need to do more automated operations and explorations, because on the digital accelerator side, this seems to be something that people are doing. And like you mentioned, there are heterogeneous systems. Every one design decision you make, there are 30 choices to choose from. And I think any one designer making these decisions is very difficult. So it's maybe makes more sense to try to automate some of this and explore it all, or automate the exploration itself so that you can find good combination points. So yeah, and I think end of the day, if you can do anything on the ADC improvement, then that's a huge thing for in-memory compute. So
Okay, thank you very much. And actually, my next question is just to follow you. So your last comments about the ADC. So we know that those like the RAM, like the MRAM, and like the ferroelectronics. So they have kind of beautiful kind of the physical characteristics and properties.
right.
Yeah, but we know that
Right.
as your slides show that so the ADC is kind of bottleneck, and I think that is maybe one reason why commercially, so like those the in SRAM seems kind of more successful, right? In those kind of the more kind of the analog in-memory computing. So
But I
this
think
is my understanding.
the SRAM companies are more successful just also in like in-memory analog computing. SRAM seems more successful for more reasons. So I think there's like, let's say there's two things. One, your yield is just going to be much better in SRAM. It's a much more mature technology.
Yeah.
So people want to take fewer risks, and in-memory compute as an architecture is already a risk. So why introduce an additional device risk and yield risk, right? People are not certain whether at 3 nanometers or 2 nanometers, RAM is still going to be a viable, heterogeneously integrated memory. And MRAM, I think the on resistance is still too low. So it's very difficult to read it quickly without disturb. So I think that's one reason why SRAM seems to be getting a lot of, or a lot more sort of, I guess, people working on it or success. Now, there is a counterpoint which somebody else pointed me to. I think Naveen, I think, mentioned this to me, which I think it's food for thought for in-memory compute generally. He said that generally when people optimize memory, they optimize memory for density and they optimize compute for a different target, right? You're optimizing compute for, say, efficiency or latency. If you do in-memory compute, then you're sort of coupling memory and compute together. And so now you need to optimize both for both, which might not be easy, right?
You're right. You're right.
So there's always a risk that that's the wrong thing to do completely, right? And we should just optimize them separately. But I think given that people have been coming to this, every 10 years it becomes hot again. So I think maybe this time we'll solve it. I don't know.
Okay. So that's a very interesting insight. Yeah. Okay. So any other questions from the audience? Okay. So then I will ask one more last question. So I think one of your slides that so some of the challenges that so right now for the memory, I think that like including the NOC, those stuffs, right? The DSC. Yeah. So actually our group, we are also right now looking into that. So I was wondering, so because you are expertise in this area, so I was wondering, so do you think that so right now kind of because I think this kind of intersection that for both the circuit community and the architecture community to look using right now, so in my understanding, so this is still this intersection is still like kind of largely missing in the landscape.
Yes.
Do you think so what is that needed to do like from the community side that should to address this issue to make the entire ecosystem can be more robust and so on?
So I think there's maybe multiple aspects. There's one aspect which is maybe extremely practical, which is that if I'm going to tape out, I need a validated IP that I can use. And I need it on that particular node that I'm taping out on. This is usually not easy, right? And so having people with the expertise to help you out very quickly, I think that is important. But usually, if I'm a PhD student, I don't want to spend time doing this sort of integration on something that is not directly going to lead to a paper.
Yeah.
Right. So I think there's a little bit of a mindset change we need, but also the availability of the resource, right? So I need to know that, hey, I can actually send my student to talk to Bo's student, and then Bo's student can get one paper as a co-author, and my student can get a better paper as a co-author, and maybe even an architecture exploration paper out of it. Right? It doesn't need to be only a circuits paper. But I think those are very complex logistical things. And on the practical side, you need access to the PDK. I need access to the PDK. And maybe we need a third party who can access the PDK and sort of help us do the integration. So that very quickly becomes a more challenging problem.
So you think that right now kind of the collaboration mechanism and it's still kind of a little bit kind of segmented that in the between among the academia and also between the academia and the industry, right?
Yes.
Okay. That's a very good point. Yeah. Maybe that the researchers in the community should work together and to find out the
Yeah,
best
I think so.
solution to
Yeah.
improve.
And there were some government programs that would help with this. So hopefully we get some of these incentives from the government that lets us work together in larger groups.
Yeah, you are right. Yeah. Okay. So Siddharth, thank you so much. So this is a very good talk, and we actually learn a lot. And thank you so much for giving us this talk, and also thank everyone, the audience, to attend our this week Rugged Efficient Seminar talk. So Siddharth, thank you so much, and look forward to
No, thank you
meeting
for
you in
inviting
the
me.
future
This was
conference.
great. Yeah,
Thank you.
of course.
Thank you. Keep in touch.
Yeah, bye. Thanks.
Okay. Thank you. Thank you, everyone. Bye.